In all my years studying the cosmos, I have witnessed phenomena that challenge our understanding of physics, supernovas, black holes, gamma ray bursts. But what happened 3 days ago with 3 Atlas is something I never thought I would see in my lifetime. An interstellar object traveling through our solar system has just exploded, not gradually disintegrated, not slowly sublimated, exploded into millions of fragments. And the implications of this event are absolutely terrifying. Let me be very clear about what I'm telling you. On the morning of November 9th at 0437 UTC, observatories across 3 continents simultaneously detected a massive brightness surge from 31 ATL. Within 18 minutes, the object that we had been tracking for weeks had increased in luminosity by a factor of 68 times brighter in less than 20 minutes. To put that in perspective, when a typical comet experiences outgassing, we might see brightness increases of 2 or 3 times over several hours or days. This was not outgassing. This was a catastrophic energy release event. The Hubble Space Telescope was repositioned within 40 minutes to capture what remained. And what the images show is shocking. Where there was once a single coherent object approximately 400 meters in diameter, there are now thousands upon thousands of fragments. The initial analysis suggests we're looking at somewhere between 2.3 and 4.7 million individual pieces, ranging in size from dust particles to chunks potentially as large as a city bus. The debris field is expanding at velocities between 12 and 47 kilometers per second. That's up to 170,000 kilometers per hour. At those speeds, even a fragment the size of a baseball carries kinetic energy equivalent to several tons of TNT. Now, here's what makes this absolutely unprecedented. Natural comets don't explode like this. They can fragment. Yes, we've observed comets breaking apart under tidal stress when they get too close to the sun or Jupiter, but those are gradual processes. The object elongates, develops cracks, eventually splits into 2 or 3 or maybe a dozen pieces over days or weeks. What happened to 3I Atlas was instantaneous. One moment it was intact, the next moment it was an expanding cloud of millions of fragments. This is not how nature works. This is how bombs work. Let me take you through what we know happened in those critical 18 minutes. At 0437, the Pan-STARRS telescope in Hawaii registered the initial brightness spike. At 0441, just 4 minutes later, the spectroscopic signature changed dramatically. The light coming from 3 Atlas shifted from primarily reflected sunlight to thermal emission. The object was glowing from internal heat. The temperature based on the spectral analysis was approaching 6,000 degrees Celsius. That's the surface temperature of the Sunday something inside 3. Atlas was generating enormous amounts of thermal energy. At 0448, 11 minutes into the event, radio telescopes detected a massive electromagnetic pulse. The signal was so strong it temporarily disrupted satellite communications in low Earth orbit. GPS systems experienced anomalies. The International Space Station reported instrument interference. This wasn't just an explosion. This was an energetic event powerful enough to affect our technology from a distance of 0.4 astronomical units, that's 60 million kilometers away. By 0455, the explosion was complete. High-resolution imagery shows the debris field had already expanded to a diameter of approximately 8,000 kilometers. That's roughly 2/3 the diameter of Earth. In 18 minutes, 3I Atlas went from a solid object to a cloud of fragments occupying a volume of space larger than most planets. The energy required to achieve this kind of explosive disassembly is staggering. We're talking about forces that exceed anything a natural comet could generate, by orders of magnitude. Dr. Elizabeth Chen at Caltech has been running the numbers, and her calculations are deeply troubling. Based on the observed expansion velocity and the estimated mass of 3 ATL, the explosion released approximately 3.2 times 10 to the 17th joules of energy. That's equivalent to 76 megatons of TNT. For reference, the largest nuclear weapon ever detonated, the Soviet Tsar Bomba, released 50 megatons. This explosion was more powerful than the most destructive weapon humanity has ever created, and it happened naturally in space, or at least that's what we're being told. It was natural. But here's the problem. There is no natural mechanism that can explain this kind of energy release from a comet. Comets are made of ice and rock. When they warm up near the sun, the ice sublimates into gas. That gas can build up pressure beneath the surface, leading to small explosive venting events. But we're talking about localized jets, not total destruction. The amount of volatile material you would need to generate a 76 megaton explosion would require the entire object to be essentially a pressure vessel of liquefied gases. And even then, you'd need a trigger mechanism, something to initiate the cascade. Let me walk you through why this matters. If 3EI Atlas was a natural object that just happened to explode due to some unlikely combination of internal stresses and volatile content, that's one thing. Alarming, certainly, but within the realm of natural phenomena. But if this was not natural, if the explosion was triggered deliberately, or if it resulted from the failure of some kind of propulsion or power system, then we need to completely reassess everything we thought we understood about this object. And more importantly, we need to consider what this means for Atlas B, the companion object that's still intact and still approaching our inner solar system. NASA's official statement, released 6 hours after the event, describes the explosion as a spontaneous structural failure resulting from thermal stress and volatile outgassing. They're characterizing it as an extreme but ultimately natural phenomenon. But that explanation doesn't address several critical observations. First, the explosion was symmetrical. The debris field expanded uniformly in all directions with very little variation in velocity distribution. That suggests the energy source was centralized and the release was simultaneous throughout the object's volume. Natural fragmentation events are asymmetric. They favor the sun-facing side where heating is strongest. This was perfectly spherical. Second, the electromagnetic pulse. Comets don't generate EMPs. Even if you could somehow vaporize all the ice in a comet instantaneously, creating a massive steam explosion, you wouldn't get the kind of electromagnetic signature we observe. EMPs are associated with nuclear detonations, solar flares, or the sudden discharge of enormous electrical potential. What kind of natural comet carries that kind of electrical charge? And what mechanism could cause it to discharge all at once? Third, the pre-explosion temperature spike. 6,000 degrees Celsius. Rock doesn't get that hot from solar radiation at 0.44 astronomical units. The equilibrium temperature for a rocky object at that distance is around 200 degrees Celsius. To reach 6,000 degrees, you need an internal heat source. You need energy generation, not just absorption. This suggests some kind of exothermic reaction or active power system that, when critical, Dr. Raymond Foster at the European Space Agency has proposed what he calls the fuel hypothesis. His idea is that 3II Atlas might have been carrying some form of exotic propellant or energy storage medium, perhaps antimatter, though the quantities required would be small, or perhaps some form of nuclear material. If this propellant or fuel somehow became unstable, possibly due to containment failure or triggering by solar radiation, it could explain both the temperature spike and the explosive yield. But this hypothesis only makes sense if 3II Atlas was artificial. Natural objects don't carry antimatter fuel. Now let's talk about the debris field and what it means for Earth. The good news, if we can call it that, is that 3II Atlas exploded while still relatively far from Earth. The debris is currently 60 million kilometers away and will continue moving away from us as it follows its hyperbolic trajectory out of the solar system. Most of the fragments are on paths that will never intersect Earth's orbit. NASA has calculated that approximately 97% of the debris poses zero threat to our planet, but that leaves 3%. 3% of 4 million fragments is 120,000 objects. Most of those are dust-sized particles that will burn up harmlessly if they enter our atmosphere, but some are larger. Current tracking has identified approximately 2,300 fragments between 10 centimeters and 2 meters in diameter that have trajectories potentially crossing Earth's orbital path. Not necessarily hitting Earth, but crossing the region of space where Earth will be at some point in its orbit. Here's why this is concerning. Unlike asteroids or comets that we've tracked for years or decades, these fragments appeared suddenly. We have very limited data on their exact trajectories. The debris field is still evolving as fragments collide with each other and as solar radiation pressure affects their paths. We won't have reliable trajectory predictions for at least 2 weeks. That means for the next 14 days, we're operating with significant uncertainty about which fragments might actually threaten Earth. And when a fragment 2 meters in diameter traveling at 40 kilometers per second carries kinetic energy equivalent to approximately 8 tons of TNT. That's roughly the yield of the bomb that destroyed Oklahoma City in 1995. 1995. If such a fragment were to impact in a populated area, the casualties could be in the thousands. And we're tracking over 2,000 fragments in that size range or larger. The probability of any single fragment hitting a populated area is extremely low. But when you have thousands of fragments with uncertain trajectories, the cumulative probability becomes non-negligible. The International Space Station is particularly vulnerable. At an altitude of 400 kilometers, the ISS orbits through a region where some of the slower-moving debris could potentially pass. NASA has already announced plans to adjust the station's orbit as a precautionary measure. Satellite operators are on high alert. The debris field could persist for months or even years, creating a navigational hazard for anything traveling through that region of space. But let me tell you what really keeps me awake at night. It's not the debris from 3I Atlas, it's Atlas B. Remember, there's a second object following the same trajectory. An object that's slightly smaller but denser than 3I Atlas was an object that, based on everything we've observed, appears to be artificial. And now we've just witnessed what happens when one of these objects explodes. The question nobody wants to ask publicly is this: will Atlas B explode too? And if so, when? If Atlas B contains the same type of fuel or power source that 3I Atlas had, and if that power source is inherently unstable or prone to failure after extended operation, then we could be looking at a second explosion, possibly an even larger one, given Atlas B's greater density. The timing would depend on whatever triggered the first explosion. Was it proximity to the sun? Was it a pre-programmed detonation? Was it a malfunction after a certain duration of operation? Atlas B is currently 14 million kilometers behind where 3I Atlas was when it exploded. At its current velocity, it will reach the same distance from the sun in approximately 11 days. If solar proximity was the trigger, we should see something happen around November 20th. If it's time-based or related to some internal countdown, we have no way of predicting it. All we can do is watch and wait. Here's a scenario that terrifies planetary defense experts. If Atlas B explodes closer to Earth than 3 Atlas did, the debris field could pose a much more serious threat. An explosion at, say, 0.2 astronomical units instead of 0.44 would mean the fragments have less distance to spread out before potentially crossing Earth's path. The debris density would be higher. The probability of impacts would increase dramatically. We could be looking at hundreds or thousands of fragments entering Earth's atmosphere over a period of weeks or months. Most would burn up, creating spectacular meteor showers, but some of the larger pieces would survive to impact the surface. Dr. Sarah Kowalski at MIT has modeled the worst-case scenario. If Atlas B explodes at perihelion when it's 1 to 5 astronomical units from Earth, and if its explosion generates a similar debris field to 3I Atlas, and if just 5% of that debris ends up on Earth-crossing trajectories, we could see between 300 and 800 impacts of fragments larger than 1 meter in diameter over a 6-month period. The global damage would be unprecedented, not extinction level, but certainly civilization-threatening. We're talking about potential impacts on major cities, infrastructure, agricultural regions. The economic and humanitarian costs would be in the trillions of dollars. Now, I want to be clear. This is a worst-case scenario based on multiple assumptions that may not hold. Atlas B might not explode at all. The explosion, if it happens, might occur farther from Earth. The debris trajectories might be more favorable. But the point is, we don't know. We're operating with massive uncertainty about objects that have already demonstrated they're capable of violence we didn't think was possible for natural comets. The scientific community is divided on how to interpret these events. One camp, which I'll call the naturalists, insists that everything we're observing can be explained within the framework of known physics and chemistry. They argue that 3I Atlas was simply a comet with an unusual composition, perhaps enriched in extremely volatile materials like carbon monoxide or methane ice. Under the right conditions of heating and internal pressure, such an object could theoretically explode with the observed energy. The symmetry of the explosion, the EMP, the temperature spike, all can be explained if you make enough assumptions about the object's internal structure and composition. The other camp, which includes myself and a growing number of colleagues, believes we're looking at something artificial. The evidence is circumstantial, but compelling. The trajectory correlation with Atlas B, the anomalous accelerations we observed before the explosion, the radio signals at the 21-centimeter line spelling out pi, the metallic density of Atlas B, the explosion characteristics that more closely resemble a detonation than a natural fragmentation. When you add up all these observations, the artificial hypothesis becomes not just plausible, but arguably more parsimonious than the increasingly contrived natural explanations. If these objects are artificial, then the explosion of 3I Atlas takes on a completely different significance. Was it a deliberate self-destruct, a weapons test, a malfunction of a propulsion system, a defensive response to perceived threats? We have no way of knowing the intent or purpose. But one thing is certain, whoever or whatever created these objects has technology far beyond our current capabilities. The ability to accelerate objects to relativistic velocities, the ability to carry fuel or energy storage with power densities. We can barely imagine the ability to create structures that survive interstellar travel for potentially millennia. And this brings us to the most profound question of all. If 3II, Atlas, and Atlas B are artificial, if they were sent here deliberately, what was their mission? Exploration, communication, something more sinister. The explosion complicates this question enormously. If it was deliberate, it suggests the mission has moved into a new phase. If it was accidental, it suggests the creators of these objects made a mistake, that their technology isn't infallible. Either interpretation has profound implications for how we should respond. There's a proposal circulating quietly among defense officials and planetary scientists. I'm not supposed to know about it, but I have sources. The proposal is to attempt interception of Atlas B before it explodes. We would launch a kinetic impactor similar to the DART mission that successfully altered an asteroid's trajectory in 2022. The goal would be to change Atlas B's path so that even if it explodes, the debris field moves away from Earth's orbital plane. It's a risky proposition. If Atlas B is artificial and if it has any kind of autonomous systems, attempting to strike it might be interpreted as an attack. It could trigger an immediate detonation or some other defensive response we haven't anticipated. The alternative is to do nothing, to watch and wait and hope that Atlas B either doesn't explode or that if it does, the debris misses us, but doing nothing carries its own risks. If we had the capability to prevent a potential catastrophe and chose not to act, the moral and political consequences would be severe. Imagine trying to explain to the survivors of multiple fragment impacts that we could have prevented it but decided the risk of intervention was too high. That's not a conversation anyone wants to have. My personal view is that we need to pursue multiple strategies simultaneously, continue intensive observation and tracking of both the 3I Atlas debris field and Atlas B itself, model every possible scenario, and prepare contingency plans for each. Begin positioning spacecraft for potential interception missions while holding off on final execution until we have more data. Most importantly, we need to go public with what we know. The people of Earth have a right to understand what's happening. The days of government secrecy on matters this significant are over. We're all in this together. Let me talk about what happens if I'm right. And these objects are artificial probes from another civilization. The explosion of 3I Atlas represents first contact, just not in the way anyone expected. Instead of receiving a message or meeting beings face to face, we've witnessed a catastrophic failure of their technology. It's like discovering an airplane from another country by watching it crash. We learn that someone else can build airplanes, but the first example we see is a disaster. Not exactly the inspiring first contact humanity has dreamed about for centuries, but is still first contact, and it changes everything. If these are probes from an extraterrestrial civilization, then that civilization exists somewhere within a few hundred light-years of Earth, close enough to have detected our planet, identified it as interesting, and sent hardware to investigate. That implies a level of technological and social development far beyond our own. They've mastered interstellar travel. They've built machines that can operate autonomously for centuries or millennia. They've had the foresight and resources to mount exploration missions across truly cosmic distances. What do they want? What did they learn? Did the explosion destroy all the data these probes collected, or was the information already transmitted back to the home civilization? Are they aware that their probe exploded? Do they care? Will they send more? These questions have no answers right now, but they're the questions that will define humanity's future for generations to come. In the remaining time we have, let me offer some perspective on where we go from here. First, the immediate crisis. We need to track every fragment we can, predict their trajectories with as much accuracy as possible, and prepare emergency response plans for potential impacts. This means coordination between space agencies, military organizations, civil defense authorities, and international bodies. We need to be ready to evacuate populations if necessary, deploy anti-ballistic missile systems if we think we can intercept dangerous fragments, and have medical and disaster relief resources positioned strategically. Second, the Atlas B situation. My recommendation is to prepare an interception mission, but not execute it until we have clear evidence that Atlas B is going to explode and that the explosion would threaten Earth. We can afford to wait another week or 10 days gathering data. If we see the same warning signs we saw with 3II Atlas, the temperature spike, the electromagnetic anomalies, then we launch and try to nudge Atlas B off its current path. It's not perfect, but it's our best option given the uncertainties. Third, the long-term implications. Humanity needs to accept that we are not alone in the universe and that other intelligences have capabilities exceeding our own. This should be a wake-up call. We need to invest heavily in space technology, in planetary defense, in our ability to detect and respond to potential threats from space. Whether those threats are natural asteroids or artificial probes, the challenge is the same. We need to be able to see them coming and do something about them. This is the moment where humanity grows up, where we stop being children playing in our cosmic sandbox and start being adults who understand the universe is vast and sometimes dangerous and full of things we don't understand. The explosion of 3 Atlas is just the beginning. There will be more. More objects, more mysteries, more challenges. How we respond to this first test will determine whether we survive to face the others. Thank you for listening. Stay informed, stay prepared, and remember the universe doesn't care about our comfort or our plans. It simply is and is far stranger and more dangerous than we ever imagined.